I'll welcome all the participants for this webinar, which is particularly focused on thermomechanical topology optimization, where we'll be making use of the mechanical tools over here, which are totally been considered to be an Ansys mechanical tool itself. So we are going to make use of the coupled field analysis system over here, or either we can create a combination of thermal and mechanical simulations to perform this optimization on whatever geometries we might have. So we are going to look like how we are how whatever the simulations that we are going to run on any kind of geometry, how those can be performed using thermal and mechanical simulation, and how they can be optimized with respect to the topology optimization tool that we already do have in Ansys Mechanical software. So first of all, I'll just introduce myself. I'm Chetan Patil, working as an application engineer for Ansys FEA at ARK Info Solutions, and below, I have even mentioned my mail ID. So if you guys have any kind of doubts or any queries related to this particular webinar or any other different topics related to FEA, then you guys can reach out to me on this particular mail ID over here. So let us just begin with this thermomechanical topology optimization webinar. So the already as mentioned in the topic itself, like we are doing the optimization based on the conditions, that is thermal and mechanical structural conditions that we are going to apply on the whatever kind of model that we might have. Based on those conditions, we are going to optimize our particular geometry, whether it might be a particular density based optimization. There are level different kind of optimizations, those are available in Ansys. So we are going to discuss about those things as well, and based on what criteria we can do thermal and mechanical optimization, how the conditions are suitable for optimization, those things we are going to discuss in this particular webinar. So first thing, like whenever we are performing topology optimization, we need to consider some kind of conditions. Those are as a prerequisite, those are already been applied on the geometry. Based on those conditions and those results that we obtain from a particular simulation, those we are going to use for the optimization, whether it might be a particular topology optimization, a particular design based optimization. So whatever it might be, it does requires a prerequisite as a structural condition or a thermal conditions to be applied. So basically what all things we can do. So as you can see in this particular slide, which is showcasing us the combination, that is the static structural results are being used in the topology simulation. So basically this particular combination is called as the structural optimization, where we are going to apply the structural conditions on the geometry under static condition itself. But all the conditions that we are going to consider in the simulation will be totally linear, because optimization doesn't allows non-linearity in the simulations. Because whenever we are going for any kind of optimization, whether it might be weight reduction or whether it might be particular other criterias based on which we are doing the optimization, those are not particularly capable of solving non-linear equations over here for the optimization. So we need to consider whatever materials we are choosing, whatever conditions we are applying, those should be totally tending towards linearity itself. Then the second combination, which is highlighted over here. So this is our particular steady state thermal simulation that is combined that is particularly using its results in the static structural simulation. So this will behave as a coupled simulation, that is our thermomechanical simulation, which we are going to discuss in today's topic basically. So how we are going to make use of the thermal results, and then how we are going to particularly couple it with the structural results, and then based on both the combination results, how our model can be optimized, and which particular regions under whatever conditions, like both different conditions, both different kind of situations we are applying on the geometry or the model, under those conditions how the model might behave, and what kind of region might get optimized over here under the conditions we are applying. So those things we are going to discuss in more detail. So over here, this is our particular thermomechanical optimization setup, and or we can say a particular workflow that is used to perform this thermomechanical optimization. And below that, we'll also discuss about the thermal optimization. So first thing that we are going to discuss is how we are able, or how we are going to perform structural optimization at the initial, then how we are going to perform the thermal optimization, what how does the particular optimization tool does behaves under different kind of conditions at the initial, and then later on we are going to combine both the conditions together, and then we are going to perform a thermomechanical optimization. See, basically optimization takes more amount of time based on the iterations, based on the amount of complexity in the geometry, and based on the conditions that you have applied. So it might take more amount of time. So instead of performing the particular demonstration in this webinar itself, I have already performed those simulations. I do have the files. We are going to discuss the particular step-by-step procedure, how the particular simulation is performed. Just the simulation results are already available with me. I'll also share that particular workbench zip file where all the particular simulations combined in a single file will be shared with you, so that you guys can even access the particular simulations that I have performed, and even all the geometries, all the contents that I have used for the simulation, those will be also available with you, so that you can explore the things, and even you can modify whatever conditions that you want to particularly apply on the model. So these things we are going to discuss. So the basic outline or the agenda of this particular webinar will be like, first of all, understanding why is it important to do the optimization process, then what kind of toolbox are available for the optimization in the Ansys software, then how does the optimization method works, basically what is the particular objectives, the determinations that we are performing the simulation for, the goal that we are performing the optimization simulation for, and like basically there are lot many things that we need to discuss, and like the overall optimization process, how does that optimization method works in the background, or based on what criterias or what conditions does the optimization happens in a particular geometry, those things we'll discuss. And then we'll also discuss the process and the workflow that we usually use in Ansys to perform a optimization simulation. Then we'll have like some three number of demonstrations over here, not the one which is mentioned over here as a shape optimization. So basically we'll discuss what is this shape optimization, but this usually takes a lot amount of time, and like in this particular session it is not considered to be highlighted over here, because we are only focusing on thermomechanical optimization, not on the shape optimization as of now. But I'll just give an short idea about what shape optimization is also like used for. Then we'll also discuss for the topology optimization process what once the model is optimized, or from the initial process itself, what all things you do need to know, and what all things you can do next once the optimization is done, and what are the available resources, those are like available free of cost, or either may require some kind of subscriptions, those are available on the Ansys websites. We'll discuss about those things as well. So we'll just begin with our webinar over here. So already the demo models are solved in the particular like previous version itself, but I'll share that particular file with you all, so that you can access it in any version. Like it can be accessed in any version greater than 2022. So basically the model or the overall file was particularly archived in the Ansys 2020 version. So it is only compatible to be opened for versions which are like upgraded than the 2020 R2. So you need to particularly open these files. So I'll just share these all files with you so that you can explore the particular simulations in them. So first thing, why is it important? So whenever we are going to do any kind of like simulation, whatever model that we are trying to develop or design, we do know for what particular purpose or application we are going to use the model for. So as it is shown over here, so basically if there are any kind of cracks, like just consider this particular example, there are cracks, for that there is some implant that has been decided, and based on that particular implant, whatever that has been designed, we are going to apply the load cases on the particular implant for which it is going to be used. And under those conditions, if it is possible to particularly optimize its shape with respect to the weight of like weight optimization, or the particular stiffness optimization, or the mass reduction, so those things will help us to particularly improve the strength as well, and even reduce the weight of the particular implant as well. So just for this particular application, why is it important we are discussing, like why topology optimization is very much important. First thing is like it will all obviously reduce the weight of the particular model. That is the major reason. It will reduce the material, it will reduce the particular cost of development. And the major important thing is the amount of energy. Basically, you can see this particular model will be used under various different kind of forces. So forces is equivalent to energy itself. So if we have a lot amount of mass that is available, that means we need more amount of forces to particularly make this model move. So if it is a little bit like heavier in weight or either heavier in mass, then we might need some extra amount of force that we need to apply over here on this kind of geometry. So if we reduce the weight or the mass of this particular geometry or implant, then basically there will be reduction in the energy that we apply on the particular model. So that means even less amount of force can even drive these particular models. So mass will behave as a directly proportional kind of term with the energy itself over here. So those conditions we are going to consider to particularly optimize. So that's why optimization is very much important. And whenever you do optimize the particular model, it can be used for like further for the particular 3D printing, and then particularly for optimization. Once it is particularly optimized based on the conditions that we do apply, then we do even particularly validate the model as well based on lot many things that we have. So we'll discuss about those things as well. So over here in Ansys Workbench, what kind of optimization tools those are available or toolbox that is available. So usually optimization is done with various different parameters. So first is the topology optimization, that is SIMP. We call this SIMP as a density based optimization solver which is available. So usually density based solver in the sense it does totally depends on the element density. So wherever it finds the particular material of the element or the particular density of the element is not capable of doing some kind of objective that we are particularly using the model for, then for those conditions it will remove that particular element from the geometry and the optimization will be performed over there. But later on, the same kind of thing is applied based on the lattice optimization as well. So this is the another thing, a particular more like advanced kind of thing or an advanced kind of optimization where the particular optimization will be done in a lattice structure. This usually takes more amount of time to do the optimization because lattice is a particular like topology, different kind of topology structure itself. So your model will be converted to a lattice structure. So that's why it takes more amount of time to generate the optimization. So that's its strength won't get reduced, but its particular mass will be reduced to a lot amount of factor. So for those particular thing, the lattice optimization is used so that even the model does looks a little bit better with in terms of topology as well. Then the third one, that is the topology optimization level set method. So this level set method is basically used to particularly optimize in terms of boundary shape modification. So over here, like it is also the same kind of optimization tool, like similar to the density, that is SIMP itself. But this particular level set method makes use of the boundary shapes to particular, you can choose whatever particular surface of the geometry needs to be modified, or it can undergo optimization. That means the particular surfaces that you will select, on those surfaces itself the material will be removed and then the optimization process will be followed. But in topology optimization it is totally different. That is in the SIMP optimization it is totally different because it is a density based optimization. So your body's density will be calculated and then those materials or elements will be removed from the geometry which do have less amount of density in them, or either they are not capable of particularly performing some conditions which are like which for particularly whatever application we are using the model, if those elements are of no use for particularly performing that kind of that kind of whatever work we are trying to make use of it for. Or either you can say if we are using some kind of thermal conditions on the geometry and we want a proper heat flow to be generated, and in some of the region if most of the particular temperature is getting stuck and no heat transfer is getting generated further ahead of it, so that will particularly affect the like heat conduction of the particular geometry. So under those kind of conditions, your particular like density based method, what it will do is it will remove the material where there is higher amount of temperature that is getting stored and is not getting transferred to some another geometry or is not flowing. So those particular elements on that particular region itself will get removed over there. So density based optimization is only eliminating the particular elements on the geometry, but in the topology optimization, that is level set method, it particularly optimizes the shape of the geometry itself based on the boundaries that you are selecting. So boundaries in the sense whatever surfaces that you will select from the boundary, those itself will come into consideration for the optimization purpose. Then later on, we do have the shape optimization, which we also call as a parameter free, or that is a morphing method. So the same is showcased over here on the particular screen itself. So this is our particular actual model, which was considered to be optimized. And under a shape optimization method, how does your particular model gets optimized? So there is no material removal. There is no particular like element removal or any particular mass removal from from the whatever model that you have. Instead, only the shape is particularly shifted in such a way that the particular body's mass will remain constant, but the overall body shape will get changed based on the conditions that you are going to use this model for. So whatever the particular forces that you are applying, under those forces, wherever there is requirement of higher density and lower density regions, that will be particularly calculated by the software, and it will particularly applied on the geometry, and your particular model will be turned into such kind of structure where you can easily find out higher amount of density to be focused wherever there is more strength that is required. So based on these conditions, you can optimize the particular shape of your geometry. And then over here, you can even set constraints. Like you can see whatever the shape of this particular geometry is there, this particular shape, for how much amount of distance or how much amount of elemental displacement should be allowed over here for the morphing process, that is for particular change in the particular shape of the elements or either the particular displacement of one of the edge of the geometry. Those kind of things can be used as constraint to particularly morph your geometry under whatever conditions that you are using it for. So these particular different kind of optimization toolbox are available. There are some new toolbox also. Those have been introduced in the latest versions, but those are still in the testing version itself. That is called as the material optimization and all. So those are still in the beta version as of now, but those as well can be used. Basically, that will guide you to find out on a single geometry how you can make use of two different kind of materials over there. And if you are defining two different materials on a single geometry, how that particular bifurcation should be done, those particular things will be showcased in the optimization process, but that is still needs to be like developed in more better way itself. So the first thing that whenever we are doing the optimization process, that you should know like how does the particular method does works over here for the optimization. So usually whenever we are doing some kind of optimization, we just know what kind of objective we are focusing on, what kind of things or goals we are trying to determine for the particular geometry or the model. So if we only are focusing on the objective, that means our particular overall simulation is an unconstrained optimization problem. Consider if I'm like optimizing my model with respect to stress. So if I want just the objective that is known to me, that means whatever the stress that is being generated in the geometry should be less than some amount of factor that is 100 megapascals. So if that is the situation over here, then whatever the least amount of stress that will be generated, under that particular value itself, I'll consider my model to be optimized. So this particular optimization is an unconstrained optimization because this will give you the optimistic result with respect to your objective, but that will affect the other conditions of the geometry as well. So until and unless you don't apply any kind of constraint to the particular optimization process, the particular optimization result that you will be getting will be only based on the objective and not based on the particular constraints or the bounds of the actual model itself. Because if you don't apply any kind of constraint, you can optimize your model in any way. Basically, if you want the best strength or the particular weight reduction to be generated for any kind of model, so mathematically it will showcase you mass should be equal to zero itself, but physically it is not possible. So for those conditions, objective should be only the particular initial conditions to be applied on the geometry for the optimization process, but based on the constraint itself, that objective should be achieved. So that particular method itself you should work on with. So over here you can see how does the constraint optimization does works. Basically, you can define different kind of constraints over here to achieve your particular optimization result. So over here, always whatever the constraints that you have applied, consider you are applying a particular displacement in the geometry as a constraint. So your body can undergo only some amount of deformation over here. So under that particular deformation, whatever the particular optimization region that is available, that is between this particular blue colored highlighted line, which is showcased over here. Rather than that, whatever the particular region that is highlighted in the blue color after this red colored line, that is your particular like over constrained region. So that will not be considered for the optimization, and only this particular region will be considered. If you apply more number of constraints, so consider even the stress that you are considering over here for the simulation. If your body undergoes some amount of stress, and if you are considering stress to be applied even as a constraint, and that particular constraint lights over aligns over here somewhere in this particular region, so it will only consider that particular optimization result itself, which comes with respect to both the constraints that you have applied, and it will try to optimize your model based on these particular regions or constraints that you have applied over here. So this will be more optimistic, and this will be more particular application suited kind of optimization that will be done. So basically there will be some different kind of variables through which you can constrain the geometry. So there are lot many different kind of constraints, but whenever you are applying constraints or whenever you are doing an optimization process, what kind of things are given to you, what kind of things you should know when you are performing an optimization is mentioned over here. So basically the given that is for the optimization process is your physics, that you should know what kind of physics that you are going to solve the particular topology optimization for. Then the geometry that you already do have, the type of geometry, whether it might be a 3D geometry or a 2D geometry. See, optimization is possible, was possible for 3D geometries itself, but now they have even introduced the 2D geometry optimization process as well. So this 2D geometry optimization process is only capable to be done with your particular density based optimization itself. Rather than that, none of the optimization process is suitable for 2D geometry optimization. Only the density based optimization can be applied over here to the geometry. Then physics, in the sense, basically you can make use of like static structural conditions. So the structural results that you are particularly focusing on, whether it might be the stiffness of the geometry, whether it might be the stresses in the geometry, the strains or either the displacements in the geometry, those things can be considered through the structural simulation. So you can consider physics as structural simulation physics, that is static structural analysis. Modal analysis can even be considered, where you can particularly optimize your model based on the frequency limits as well, because frequency totally controls the stiffness of the model itself. And if the stiffness of the model is very high, that means we can consider the strength of the particular geometry is very high. So we want maximum amount of frequency to be achieved for any kind of geometry to have maximum amount of stiffness. So those kind of things can be known when we perform a model analysis on the model. So even physics does allows model simulations as well. And the only thing that is left out is thermal simulation. So thermal simulation is also allowed over here to be done for particularly performing a topology optimization, where the major important parameter is your thermal conductance. So basically thermal conductance does lets you know how the heat flow is getting generated, and to achieve a better kind of heat flow within the overall geometry from hot region to cold region to be achieved very smoothly, how this particular thermal conductance can be achieved. So usually we consider a larger thermal conductance value for better heat flow from within a particular geometry based on its material property. So if the thermal conductance value is very large, and that time we can consider the particular heat flow is very better. If it is less, then we can consider there is less amount of heat flow within the particular geometry or the within the particular material. So those considerations can also help you with the topology optimization to achieve a better heat flow as well. And the structural conditions are therefore available itself, like maximum stiffness is the only parameter that we usually do the topology optimization for. And based on the particular stiffness achievement, we are focusing with reduction in the mass or the volume itself. So whenever the particular density is less, the volume and the mass will be also particularly less for the given geometry itself. Then the design space basically will help you with selecting which particular regions from the geometry should be like excluded to be not included in the optimization process, and which particular part of the geometry should be used for the optimization. You can decide those things. So that is available to be done in the design space. Then based on the loads, boundaries, boundary conditions and material, you can determine what kind of particular results that you are interested in. And there are all the methods that you can apply for the topology optimization process. So you can see you can apply SIMP method, LSM method, that is level set method. Then you can make use of shape optimization as well, and even the particular lattice structure optimization method as well. So all these kind of methods are available to apply. And the major reason of whatever the given parameters are there to do the optimization process is to particularly determine for whatever objective we are doing the optimization for. So we need to know for what objective we are working with the optimization process, whether we want maximum stiffness, we want reduction in the mass or volume, we want higher frequency, so that particularly frequency will give us more amount of stiffness in the geometry, or reduced in the frequency so that the particular stiffness will also get reduced. Then thermal conductance as well if you are doing a thermal simulation. But all these conditions, all these particular objectives that we are doing the optimization for should be subjected to some kind of constraints, so that your particular objective will not will be not misguided or will not be under constraint. So that whenever you are trying to define some kind of stiffness, so there should be some amount of actual mass should be available. It should not overpass the particular deformation in the geometry, or it should not go beyond some amount of stress in the particular geometry or mass in the geometry. Those are some constraints that you need to apply whenever you have some kind of objective to be satisfied through optimization. So this particular subject to constraints, so based on the particular structural optimization, you can do particular mass reduction. So that can be considered as a mass constraint over here. You can apply displacement as well as a constraint. So you can, if you are expecting a displacement less than 0.06 mm, you can define that as a constraint over here. And you can even define stress as well, stress, strain, and other parameters as well to be a constraint. So whenever you consider any of these particular parameter to be a constraint, these are called as the response constraints over here. So based on your particular response constraint, the objective should be achieved, and through that itself, the particular optimization is supposed to be performed. Then later on, if you are performing a particular model analysis, that is for frequency based simulation, then you can particularly define these as well as a constraint over here, that whatever the first mode that should be achieved, or a 20th mode that should be achieved, whatever mode value that you are considering. So if there is a particular limit within which your particular model should get optimized, you can define that particular frequency range over here, or either a frequency value over here as a constraint, and your model won't reach to that particular frequency, or will try to always be greater than that particular frequency itself, so that the stiffness of the geometry will not be less than the particular constraint value. So whenever you will optimize the model, so its stiffness will not be less than whatever the constraint that you have applied. So that will particularly increase the strength of the particular model itself. Then even there are some kind of constraints that you can consider to be applied with respect to the manufacturing process. So these are the particular symmetry process where you can particularly consider same kind of structures to be generated whenever the optimization process is done. So that like the body will be mostly like considerable kind of geometry. There will be no irregular kind of structures, smooth kind of surfaces will be generated under a symmetric condition. So that will be applied as a constraint over here. Then you can even define like minimum member size as well. So basically these constraints are used to particularly generate the optimization process on the model with respect to very smooth kind of finishing as well. And even whenever the optimization is done in some of the region, if there is very least amount of material or either geometry that is available, that should either be increased based on the particular constraint like minimum member size. Because whenever you are taking the optimized model for the 3D printing, there is some amount of limits with 3D printing the model as well. So if the particular whatever 3D printer that you have, if it only creates the 3D printed model of sizes greater than 0.2, so that means your particular geometry should not have any particular region where the size is less than 0.2. So you can decide even the minimum member size as well in the geometry based on which the optimization will be generated. And even you can control the center of gravity as well, so that the manufacturing process, kinematic simulation, kinematic results of the geometry, the impact results of the geometry won't get affected. You can define the limits of center of gravity where it should be located based on the optimization process as well. So all these constraints, all these objectives, these particularly help us with getting the actual optimized model which is required for the particular application that you are using the model for. So all these things needs to be applied in a precise way, then and then only the optimized results will be provided to you. So usually this workflow that we do follow for a particular optimization process, where we do have an actual model that we have already designed. Then later on, when we do perform some kind of simulations on that particular model, we do find out wherever the particular region that is of no particular use, because there is no particular like much amount of deformation or stresses those are being generated. These elements are just increasing the energy that is required to particularly make the model move. So basically this particular region can be removed. Once that is optimized, your model might look something like this. Once that is particularly generated, you can take that model for the particular validation purpose. And once it is validated, you can particularly 3D print it or either manufacture it. So the particular process is also followed in the same way in the Ansys workbench workflow. So over here, you perform some kind of simulation. So as of now, it is showcased over here that firstly the model analysis is performed. So based on any particular frequency limit, you might have done the optimization over here. And once you particularly get the optimized result for your model, then based on that particular result, you can extract the data into two different forms. That is, you can transfer the design for the validation design validation system in terms of either geometry itself, which is showcased over here in terms of C, or either you can transfer your particular design validation system to a model, so that whenever you transfer it to model, you can re-perform the particular static structural analysis, where you can find out whether the optimized model is behaving in a proper way under the same kind of conditions that we did previously applied when the model was not optimized. So under those conditions, how the model does behaves, and whether whatever the particular optimization has been done, that needs to be validated, and it can be validated through this particular process over here. So this overall thing can be performed. So usually we do link the solution of one system to the setup of the another system. We call this as a linking of 6 to 5 system itself. So we'll look out how this particular linking is done, how to particular transfer the data from one system to another. All those things we are going to discuss when we'll go for the demonstration purpose. So the first demonstration that we are going to have over here is on the pump housing. So basically, this is the particular model that we do have. This is actually a single kind of geometry itself, which is available, from which we are only focusing on this particular inner region. So as you can see, this particular like region which is highlighted over here, this is the only region on which we are particularly focusing to generate the optimization on, based on whatever the kind of structural conditions we do apply. So this particular first simulation will be your structural simulation optimization. This was related to the shape optimization that we are not going to focus in this session. So the third will be your thermal optimization, where we are going to apply some kind of like thermal conditions on the geometry, where we'll keep one of the geometry to be particularly under constraint, in the sense totally being less amount of heat to be generated on that region, and we'll try to find out. So as you can see in this particular image, whatever the result that has been generated on a simple cube kind of structure, because usually thermal optimization is not into much consideration. But over here, you can do those kind of simulations. But as of now, just for an example purpose, I have taken this simple kind of cube structure over here, where on the top surface, I'm considering this particular surface to be applied with very least amount of temperature, and on all the particular vertical walls, I'll provide some kind of heat flow over there. So that particular region, like that particular conditions will generate some kind of temperature flow on the heat flow on the overall geometry. And based on that particular heat flow itself, we want the minimized thermal compliance. So basically, minimized thermal compliance will increase the particular stiffness in the stiffness of the particular geometry, because compliance is directly, is inversely proportional to the stiffness of the model. So whenever we are considering the compliance for the objective purpose, at that time you can consider you are using stiffness to be also the same, like objective itself. So whenever you define compliance over here for any thermal condition or structural condition, it should always be minimized itself. So whenever compliance is minimized, that means stiffness is increased in the particular model. So even you can apply some kind of response constraints over here for the mass of the geometry. That means somewhat 50% of your mass should be restrained. So whenever the optimization process will be carried out, only 50% of the mass from the geometry, even if though there are lot much amount of region that needs to be removed, but if not that particular amount of region is supposed to be removed, only 50% of amount of the overall body part should be removed. That can be applied as a constraint over here. And under those constraints, how does the model will get generated after optimization? We need to find out those things. Then this is a particular optimization process where we are going to combine the thermal and the mechanical conditions together. This is the particular objective of this webinar, that is thermomechanical optimization of this assembly model. So this is an assembly model where we do have multiple number of parts, from which we are only focusing on the center part of the geometry. So when we'll go for the demonstration, we'll discuss about these things in detail. Okay. So I'll just launch my workbench screen over here, so that we'll directly jump onto the workbench screen itself for the demonstration purpose. Just give me a second. Okay, so already I have solved this particular optimization demonstrations, whatever I have mentioned, the 4 demonstrations, from which I have performed the 3 of them over here in this particular file. I'll share this file with you all. Like, why I'm not solving this right now is, whenever I'll take it to the solve, like it might take more amount of time to get the results. So it will particularly waste much amount of time in just getting the solution for one of the model, and we don't have much amount of time to spare over here. So that's why I have just solved the file, but we'll go through the overall process so that you don't miss anything that is particularly important to be known for the simulation. So over here, first of all, I do have the structural optimization optimized kind of model over here. I do have different kind of structures that I have used. So over here, there are 4 different number of simulations that I have performed. First 3 are the 3D body based kind of like optimization that we have done. And the last one that is available over here is on a 2D surface geometry. So how the particular 2D optimization is done, we'll look out into that particular thing as well. But over here, these three are the structures that we are focusing as of now. The first thing was related to the pump housing. The second was this thermal simulation was related to the cube box. And this particular thermomechanical simulation is related to your particular assembly model that we are going to see. So first of all, I'll just launch my first simulation that I have performed on the pump housing over here. We'll discuss what all things that have been done. So as you can see, I have particularly performed the static structural simulation over here, and I have just dragged and dropped the particular structural optimization tool as well on it. So over here, you can find out the structural optimization. I have just dragged and dropped it on the solution over here, and it has created such kind of links between both the particular analysis systems. Now, once you create such kind of linking between the analysis systems over here, you might find out your particular static structural to be connected to the topology optimization over here. So first of all, we'll go to our particular geometry. So when you come to your geometry, so as you can see, this particular body part, which was a single geometry that was available, but for the optimization process, you should always know which particular geometry you are able, like you are particularly focusing on optimizing, which particular region of the geometry needs to be optimized and which particular region needs to not to be optimized over here. Because if you optimize this particular bottom and top regions as well, these bodies might be connected to some other geometry. So that's why this particular region might get affected. The surfaces on the geometry might get affected. So whenever you consider these surfaces not to be included in the optimization process, that means you are particularly neglecting this region itself. So that's why what I have done over here is I have divided this particular geometry itself into three number of parts. So one is the bottom part. So I have created two different planes on the surfaces of the geometry, and I have just split this particular geometry into three number of equal part. So from which we are going to use this particular part itself for the particular optimization process. This particular part is assigned to a linear material over here. As I did mention, topology optimization doesn't allows you to particularly go for non-linear kind of optimization process. So this won't particularly make use of the non-linear kind of results. So you can make use of the linear material properties itself for the simulation. So as of now, structural steel is the only material that I have applied over here to all the geometries, but from which we are only performing the optimization on this particular geometry. Now this particular geometry is also connected with this particular top surface and bottom surface of the model. So this is an actual single part itself. When I'm particularly splitting it, that means these are three different components now. So each component should be totally connected to each other. So basically that's the only consideration over here, that both all these three systems to be totally fixed with each other, totally connected to each other. So that particular condition can be applied through connections over here. But as you can see, there are no connections. In connections, we could have applied bonded kind of contact between all the three bodies over here. But even if I'm applying any kind of contact between the geometry, if it is only the linear contacts that I can make use of, like bonded or no separation, that means I'm making use of a linear kind of condition itself, because non-linear contacts are not suitable for optimization process. So you need to go with linear kind of contacts itself. And over here as well, I wanted to make use of a bonded kind of contact, which is also linear kind of contact region. So if I'm defining a bonded kind of contact, it is always better to go with share topology option itself. So in share topology, you won't face any particular thing to be done over here in the Ansys Mechanical. Automatically, all the particular geometries will be connected with each other. So you don't have to even worry about the particular connections in the geometry and even the particular node connectivity between the geometries. So that is the particular process which is used over here to do the optimization process through the shared topology optimization. So these bodies are connected with each other and will behave as a single body itself, but just are splitted to do the optimization process. Now next, doing the particular meshing on the geometry over here. So as you can see, only the region which is major concern for the optimization purpose. So that particular region itself needs to be optimized with better kind of elements. Other regions which are not of your particular concern, you can neglect them. You can create any coarse kind of mesh as well. That won't particularly affect the simulation. And even whenever you're doing a particular optimization on any particular model, it is always recommended to create similar kind of element, uniform kind of elements on the overall geometry that you are using for optimization. Because whenever there will be uniform kind of elements on the geometry, whenever the particular removal process will be done, whether it might be based on density, whether it might be level set method, or whether it might be any different kind of method that you might be using, those will particularly remove the material in a better way, in a smooth way itself. So whenever there will be irregular kind of meshing that will be done on the optimizing model, then it will take more number of iterations to do the optimization process. And based on even the constraint as well, it will be very much difficult to obtain the converged kind of optimized model for you. So all those things do affect a large. So over here you can see I have just applied a body sizing over here on this geometry, and both the geometries are left out to be particularly default itself. So under those conditions I have generated the mesh. And even as I did mention, due to the shade topology option, there is mesh connectivity between all the geometries. So as you can see, there is just a single node that is connected between these two geometries, that is the bottom one and the middle one. And even the same condition is available for even the top one and the middle one. So this mesh connectivity does also matters a lot whenever you are using a single geometry for the simulation, or either you are using multiple bodies but those are connected with each other, should have mesh connectivity between them, so that results or data will not be particularly get differently generated with different kind of simulations. So over here, now once this particular meshing is done on the geometry, if I would go further to the name selection, I have created some kind of name selections over here. So first two name selections are where the particular frictionless supports needed to be applied on the geometry. So these two regions are your particular frictionless support regions that I have just created a name selection so that my selection process will be easier for the supporting purpose. But later on I have even created one selection over here. So what is this particular selection that I have made? So this is your particular selection, which elements from the particular geometry you are considering to not to be used for the optimization process. These particular elements which are present on this particular top surface and bottom surface of the geometry, those are connected even with your particular top region and bottom region of the geometries, two different components. So if the particular elements will get removed from these particular regions of the geometry, then that means your particular connectivity between the bodies will get break. So that's why I have considered these particular regions of the geometry to be not optimized, or either not considered to be optimized. Even though if this particular region which is present over here, this gets optimized, that doesn't matter. But this particular region which is present on this particular which is particular the contact region of both the bodies, there the particular element should not get removed, because the connectivity will get affected over there. For that purpose I have just selected this particular region over here. So how this selection is made basically is through the worksheet which is available over here. What you could do, you could just select the particular surfaces wherever you don't want to remove the elements, you don't want to make use of the elements from the geometry. You can just select those particular regions from the geometry, right click on them and create name selections. First of all, once you click on the name selections, some such kind of screen will be visible to you. So as you can see, such kind of name selections have been created over here. Once these name selections have been created, you can just turn on the worksheet over here. So there are two different kind of options of scoping, that is geometry selection and worksheet. So always go with worksheet if you want to create, if you want to select elements from the particular geometry. So once you consider worksheet over here, there is an option to particularly add one row below whatever the selections that you have made, that is 8 faces on the geometry. which are supposed to be applied with frictionless support. But as of now, for this selection, we might have selected different number of faces. So once those faces were selected, so as you can see, these particular faces were selected over here. You can just, once those faces are selected, you can just right click on them and click on add. Once you click on add, so you can just see such kind of one row will be added below it, and you can just click on convert to. Once you select the faces on the particular geometry, then those faces will be available in the first row, and then later on below that particular row you can just select convert to. So once you click on convert to, you have different kind of entity types that you can convert your particular face selection to. So the first row will showcase you the face entity type, and in the second row, when you click on convert to, you should select this particular mesh element. Once you select this mesh element over there, then all the number of elements those are located on the surfaces that you have selected will get automatically selected over here, and for that the particular worksheet will be created in terms of name selection. Once you select all these particular elements on the geometry, then those elements you can use it further for the optimization process, and you can define this particular region of the geometry should be excluded from the optimization process. So over here, these name selections have been created. Later on, I have applied some kind of forces. So this force is applied in the X direction over here. So I have used a two-step analysis over here basically. So two-step to apply two different kind of loading conditions. So one is in the X direction and another one is in the Y direction over here. So these two loading conditions I have applied based on my particular application of the model. So you can see I have applied three frictionless supports. So two of them are the particular name selections that I have created, and the third one is at the bottom of this particular surface over here. And I have applied both the loading conditions with a two-step kind of analysis settings. So once all these settings have been applied, once all the number of forces have been applied, I just need to solve the solution. This solution of static structural simulation won't take much amount of time. So as you can see, it just took 39 seconds to solve this particular simulation. But the optimization process just takes a lot amount of time. Now over here, if I would go to total deformation, you can easily find out that this is the particular deformation in the geometry that has been generated, which is 0.19 mm. So whenever I'll go for the optimization process, now whatever constraint, if the objective of my particular simulation is to optimize this particular model where the material removal should be done from the geometry, wherever there is less stress and less amount of deformation, those regions will be considered to get optimized. But whenever you are doing the optimization process with the objective of reduction in mass, but you need to consider the stress should not be beyond whatever the particular limit that you might have considered, or deformation should not get increased based on whatever the kind of value that you have considered. So those should be applied under constraints. So under constraint, whenever you define a particular value for the deformation or the stresses, the value should not be equal to these values which you have got from the static structural. If you define a particular constraint which is equal to this particular value that you have got from the static structural simulation, then at that time already this particular value has been reached under the conditions that you have applied. So whenever it goes for the particular optimization process, so what it will do is it will just keep on iterating the solution, but it will not give you any kind of optimization on the model. So for that particular process, you need to define a value larger than this particular total deformation that you have obtained. So then and then only it will show you the optimized model. So once you drop the particular optimization system on the static structural solution, you will get such kind of interface in front of you. Now this particular optimization settings have been already applied over here. First of all, the analysis setting. So usually we don't make any kind of changes in the analysis setting, but if you want some more number of iterations or some less number of iterations to be performed, and those kind of settings you can apply over here. The accuracy of the solution does depends on you. So all these factors can be considered by you itself. So manufacturing constraints, then your particular minimum member size, all these constraints can be applied. If you have better knowledge related to optimization of your model, you can just change it. But mostly the automated or the default settings does works well with your particular density based optimization. When you go with different kind of optimization, you can change these particular factors based on your particular application as well. Now the next thing is your particular optimization region. You have selected one body for the optimization purpose. So this is our particular geometry which we have selected, which is this particular middle section for the optimization process over here. Later on, your particular exclusion regions will always be the boundary conditions. That means from your overall geometry, even though you haven't selected the particular bottom and the top geometries for the optimization process, but you can select the boundary conditions over here, or even you can select the geometries as well, or the name selections as well. But boundary condition is a better way initially to choose, because based on this itself you can particularly optimize your model, so that whenever your particular model will get optimized, even if the overall model gets optimized, these particular boundary conditions wherever you have applied, those regions will not get affected with it. Then here are the particular optimization options that you can select. So as of now, we have selected the density based. Similarly, you have mixable density that is available. Then the latest one, that is material optimization, is available over here. Then topography optimization is the particular shape optimization process itself once again. So these two are the same kind of optimization processes. Then lattice structure optimization and level set based method optimization is also available. All these kind of methods are available. You can choose anything based on what conditions you want to optimize the model. So as we did discussed, how does the actual all the particular optimization method does works. Based on that, you can just choose any one of them over here. So as of now, density based method doesn't take much amount of time to optimize it. So that's why we have just selected this one over here. Now inside this exclusion region in the sense like whatever the name selections we did considered over here, this particular element should not be excluded from the geometry. Like this not should be included in the geometry while during the optimization process. So over here in the exclusion region, you can just select this name selection option. And then over here, you can define whatever the elements that you have considered in the name selection to be selected over here. And those particular selection regions will not get optimized. So those will come into the particular non-optimizable kind of region. Once this is done, you just need to define the objective as well. So in this objective, you can see over here. So there is a compliance that has been defined. In the similar way, you can find out volume, mass, or either stress, or either any criteria based on which you want to particularly define the objective. So criterias, you can create whatever criterias you want to define. So there are lot many number of criterias that you can create. So based on those criteria, you can define the particular objective as well. So as of now, we haven't selected any criteria over here, so that is not applicable to be applied. So if we are going with the compliance itself, you can see the compliance goal should be always minimized, so the stiffness will automatically get increased in the model based on the conditions. So structural simulation we have applied, so it is a two-step analysis that we have done. So all those things have been considered over here, and we have even applied a response constraint, that is a particular mass constraint that we have applied over here. That this constraint does defines that your particular mass after the optimization process should not go less than 50%. That means minimum 50% of mass should be retained back again. So instead of optimizing the overall geometry, we are only optimizing 50% of the mass of the geometry. So once this particular simulation gets solved, so you can see this solution has taken somewhat 13 minutes of time. So over here, this is not showcasing me the graph over here, which is achieved with respect to the objective and the mass response criteria. Actually, the result file might have got a little corrupted because of saving it in different kind of formats. So you guys just can run this particular simulation once again, and you can just find out this plot which is generated over here. Then once the particular optimization process is done, you can see how the particular optimization is generated on the model. So this way you can particularly achieve the optimization that has been generated on the model over here. So it has reduced more than 50, like 40% of mass from the geometry itself. So you can even check whether how much amount of particular density has been removed from the particular geometry, and how many number of iteration did it took actually to generate such kind of particular optimization on the model. So it took somewhat 18 number of iterations. The original mass of the geometry was something 2.4187 kg, but the final mass over here is 1.7921 kgs. So basically the overall geometry mass is available, from which only this percent of mass has been generated over here. That means not 50% of mass is removed, but only 25% or either 26% of mass has been removed from this actual geometry. So you can see you can optimize your model for a little bit more kind of weight as well, more kind of forces as well, and you can even reduce its mass to a little bit larger level. So your model can still sustain that particular loading condition, I guess though. So as you can see over here, this particular file has been generated in very like irregular way over here. So whenever you take it further for the validation purpose, it might create some kind of issues with the geometry meshing and all other things. So what you can do is either you can export this particular model, whatever the optimized model that you have got, into a particular STL file, which was the previous option that was available. But now there is an option to smooth, like you can export this particular model into a smooth STL file. This will particularly reduce the post processing of your geometry. So whenever you export this with a smooth STL file, it will automatically like regenerate these regions with some kind of better kind of faces over here. So that will not affect the particular geometry like model as well, but even it will help you with the particular meshing as well. So this way you can do the particular structural meshing at the initial. In the similar way, you can just go with the other meshing processes. So I'll just uh, go with the thermal meshing, thermal optimization process, and then we'll go to the thermomechanical one. So I'll just open this Ansys Mechanical once again for the thermal optimization process. So this particular process has been conducted on a 3D model itself, which is a cube kind of model which I have used over here. Just I have divided the top surfaces into three different parts where I'm considering this particular part to be isolated or either to be set to a room temperature over here. So this particular temperature at this particular region is totally isolated. And rather than that, like I have used a heat flow that is of 0.1 watt on all the vertical walls over here. And based on that, now I have applied the particular conditions over here on the geometry. So the geometry doesn't have any modifications with it. The particular material is also the structural steel itself, where we are only considering the particular thermal conductivity property, isotropic thermal conductivity property, which has been defined to the structural steel. And then the meshing has been done on the geometry over here. So this is one of the standard meshing. So that's why it will generate a better kind of optimization for this particular model. Once this is done, now if we would go with the particular solution, because already you can see there is no particular change with the analysis setting. The setup with thermal simulations are with little basic and very much easier kind of things. So over here, all the settings have been applied properly, and based on this, the temperature results have been generated over here. So wherever the particular least amount of temperature that is available, that is 0 degree, over here you can consider there is better kind of heat flow because there is much amount of variation with the temperature. This region which is present over here at the bottom is having is particularly carrying very high amount of temperature over here. These elements which are located over here are carrying very high amount of temperature. That will particularly affect the heat flow because there is no further heat flow that is being generated in from these particular elements which are present over here. So that's why these particular elements can be removed over here, which are not particularly making use of the particular temperature to get flow from hot region to the cold region. So there is no better heat flow that is being generated due to these particular elements over here. So even if though you remove these particular elements over here, for a better heat flow, you can just consider these number of elements where there is particular better heat flow that is being generated. So if you would go to the heat flow results over here, you can see which particular regions of the which particular elements or region of the geometry is considered to be particularly having better kind of heat flow into them. So these particular regions are there. And when you do apply this particular condition for the optimization purpose, over here, we don't change anything with the analysis setting. We have considered this particular optimization of the model to be done. And this is also density based optimization where we are considering the overall geometry itself. And just we are considering this particular phase of the geometry to be excluded because there is no particular temperature that is applied over here. So we are considering this particular region to be not considered for the optimization purpose. So once these are done, you can just go to the optimization where you can see the thermal compliance is considered over here, which is your particular thermal conductivity, which needs to be minimized. And if you would go to the response constraint, once again, the mass itself is applied over here to be the response constraint. And then you can just go to the solution over here to check your particular optimization that has been generated. So if I would just go to the result to have a undeformed geometry as well, you can see how your particular geometry does look like. Not this one. So we'll just go with even the show elements itself. So over here you can see now how the particular optimization process has been done, and even how the particular elements from the geometries have been removed over here. So this is one of the best way to particularly optimize your model, because over here the structure of the geometry is also very better. Based on your particular element quality, the particular optimized results will also be that much amount of better itself. So this will not require any particular post processing with the geometry. You can directly use it for the validation or the 3D printing process. So over here, it has particularly removed over here, the actual mass was like minimum somewhat 6 point something kg in terms of e raised to minus 2. So over here, percent mass of original, that is 45% of mass itself has been retained over here. So instead of generating the particular 50% of mass, it has only retained the particular 50% of mass over here. So minimum it has considered to be 0.4965. So usually this particular optimization process is done based on the particular value of the density of the elements. So over here you can see it has only considered the value till 0.49 itself. That is the topology density. Basically the elemental density is considered to be present on a range of 0 to 1, 0 to 1. So whenever your particular like density of the elements is less than some of the limits, those have been considered over here, then those elements will get removed from the particular geometry. So if you want to check what is the actual particular density consideration over here of each of the elements, you can just go to the user defined results and you can check which particular regions are generating very least amount of element densities over here. So based on the particular results of your total heat flux and particular temperature, there are some of the elements which are generating very least amount of elemental densities. So these particular elemental dense elements are of no particular use to particularly heat flow from one region to another region. So for that particular purpose, this constraint has been overpassed over here, and based on that particular thing, this optimization process has been carried out. So you can just go with this particular way as well. You can just change all these conditions in this analysis setting as well. You can set all these particular parameters over here, and based on that your particular topology optimization will be carried out in a more better way. In the similar way, we have gone even for the thermomechanical one as well. So if you would open this thermomechanical application, you guys can just do one more thing as well. When you will have this particular file, you guys can just go through each of the particular simulations. You can change the conditions and check how the particular model does behaves under different kind of optimization methods. So you will have a better idea about each of the different types. So over here, this is the assembly that we are using for the simulation. So based on this particular model, we are only considering this inner geometry to be optimized. So if I would just go to the geometry section, these are the three geometries which are considered over here to be considered for the optimization process. But between all three, this just one single geometry is going to be optimized. So for this, the material is still linear. Now, instead of applying a particular like share topology option, I haven't applied that particular option over here. So there are some contacts those have been created between all these three bodies over here. So all these three are the like all these two contact regions are the bonded contact region itself. That is your particular linear contact region. Then the meshing has been generated on the geometry. You can see these two bodies are generated with very coarse kind of mesh. Just the inner body which is available over here, which needs to be optimized in better way. I have created a hexaedral kind of meshing, which is very much like better for generating optimized results for any geometry. So usually we do prefer generating hexaedral kind of elements with uniform kind of size on the geometry for better optimized results. So over here, I have defined different body size itself for this particular model. And other than that, all the particular other geometries are coursed over here. Now over here as well, from this particular geometry based on the conditions that I'm applying. So you can see what kind of conditions that I'm applying over here is I'm just applying some like temperature values over here. So there is a particular temperature which is highest present over here, that is 250 degrees Celsius. Then there is one another temperature that I have applied on the inner geometry over here. This is 50 degrees Celsius. And then there is a particular least amount of room temperature that has been applied on this particular end of the geometry. Now overall geometry specific like overall thermal specifications have been applied on the particular geometry over here, and even I have created name selections as well. So whatever the surfaces, those are supposed to be considered to be not used for the like for the optimization process, those have been selected over here. So as you can see, these 27 number of surfaces have been selected from the inner geometry itself, because we are only optimizing the inner part. Now only these particular surfaces which are present on the outer region of the geometry, those itself are considered to be optimized, and inside whatever the volume that is present inside this region will get optimized over here. So those itself have been considered, and other than that, whatever the remaining surfaces are there, those are particularly excluded from the optimization purpose. So over here the selection is still done in the same way. First of all, this particular region has been duplicated. Once it is duplicated, you can change its geometry selection to name selection over sorry, worksheet over here. Once you make it as a worksheet, you will have some such kind of interface in front of you, where you will first of all find out your particular first like selections that you have made in the first tabular data, where you will find out the faces that you have selected on the geometry, and this particular faces that you have created through name selection are the excluded surfaces from this particular geometry. Now, whatever the elements those are present on this particular geometry are not supposed to be considered for the optimization process. For that, I have used this particular add to. So I have just right clicked and added over here one more row where I have used the convert to option. So once this is converted, I can go with mesh element over here instead of face. So whatever faces those were selected, convert those faces into mesh elements over here. Now, all these particular surfaces which were present, those were considered to be like having some kind of elements relevant to them. So those itself have been selected over here, and a total of 7,464 number of elements have been selected from this overall geometry. Once all these number of elements have been selected, now if I would just go to the particular like steady state thermal conditions, these conditions have been applied. Now based on the solution that I have been generated on the geometry over here, so you can see how the particular geometry has been generated with just a second. Yeah, okay. So you can see how the particular temperature plot has been generated on the overall geometry. This particular region of the geometry is supposed to be considered to be optimized. Now over here, there is no much variation on the inner side of the structure, but if you would check the heat flux, so you can see this particular blue colored region. Those are the regions where there is no particular heat transfer that is getting generated. But from there as well, there are lot many regions that we have excluded from the geometry. So if I would just go to the solution and hide this particular geometry and see the heat flux over here, you can see some of the regions those have been generated with higher heat flows or heat fluxes. Those have been particularly like even considered to be excluded from the optimization. So there will be no chances of these elements or this particular region to be included in the optimization. Only wherever you find out the excluded regions and blue colored elements to be present, there itself the particular optimization process should be carried out. But this is just with respect to your particular thermal conditions. Now, whenever you want to go with thermomechanical simulations, you need to make use of both the conditions together. So over here in the static structural, we have applied the particular like loading condition over here on the geometry, which is 10,000 Newton of angular load that we have applied on the geometry. And there is a fixed support that I have applied on the geometry over here on the another side of the loading condition. So over here, those two conditions have been applied, and even whatever the results that we did get from the thermal simulation, those have been imported over here in terms of imported body temperature. Now this particular data and whatever the structural results that you will be combinedly get over here with the model, those will be used and particularly generated the results with. So this is the amount of temperature, total deformation that you will get from the simulation. So you can see these particular regions from your particular geometry. If I would just hide any one of the geometry part, so you can easily find out this particular thing. So this particular region, wherever there is total deformation that has been generated very less, that particular region is even in the included region of the optimization. So that particular region might come into particular consideration. Even the stresses on that particular region might be less or either might be very high. We will find out those things after the optimization process over here. Now in the optimization process, in the optimized region, you can see they have excluded this particular geometry because you just need to apply any boundary condition over here. And then whatever the exclusion regions that you have defined, that was your particular selection that you did made in the name selection over there, that has been even considered to be excluded over here. After that, the objective was two different things. One was your thermal compliance and your particular structural compliance. So both the things have been considered over here in terms of your objective, and response constraint is your same mass itself. So usually we do apply mass as the response constraint most of the time so that your particular mass will not get totally reduced from the geometry. So these constraints we have applied and these objectives were being selected over here to be applied on the geometry. And then based on that, if you would go to the optimized model, you can find out these particular regions to get optimized over here. So whatever the regions that you did selected not to be optimized have not been optimized, and you can see how the particular optimization process has been carried out based on wherever the total deformation is larger or wherever it is smaller. Those particular regions and heat flow regions have been considered to be particularly not optimized, and wherever the particular suitable region was there from where the material can be removed, which won't affect the heat flow, that particular region itself has been modified over here. So this has even provided a better kind of structure as well over here due to your hexagonal kind of elements. So whenever you will go further with the particular validation purpose, you will have the model ready with you. You don't have to modify anything with the geometry over here. So this way you can particularly perform the thermomechanical simulations for the optimization process. You can use any condition related to thermal and any condition related to structural and combine them for particularly performing the optimization process. So I would recommend if anyone is going to practice it, then you can just go through the optimization type. You can change this particular topology density based to level set based, and you can check how the particular differences might occur. In level set based, you just need to define the particular regions in terms of boundaries. So over here, we are not defining the particular, we are directly defining the exclusion region. The same way we define the particular inclusion regions as well. Inclusion region in the sense you will define the particular bodies or the particular structures from your geometry to be included in the optimization purpose. So on those surfaces, those particular surfaces which you have selected itself will be considered for the optimization purpose. So this way you can perform your thermomechanical simulation. I'll just showcase you one more thing which is related to the 2D kind of simulations, how and what kind of results you can consider for a 2D model. So you can see this particular simulation has been carried out in a 3D analysis type itself, but the model that we have used is a surface model over here with some amount of negligible thickness. So let's just open that particular model and showcase what kind of result you can expect from a 2D kind of simulation for density based optimization process. So over here, this is my particular geometry which I have used over here for the simulation. So if I would go to the mesh, there is very least amount of thickness that has been provided to it, which is nearly equal to, I guess, 0.1 mm itself. So I have provided very least amount of thickness to it. And then the meshing has been generated with a mapped face meshing because the divisions I have made over here on the surfaces. So you can see this is the same kind of representation of a cuboidal model, but just in a 2D surface kind of way. So over here, the conditions will still remain the same. Just this surface will have some isolated region that is temperature nearly equal to zero or room temperature. And then there will be a particular heat flux that I have applied on this particular surface of the geometry. So if I would go to the particular temperature, you can see the temperature at this particular smaller edge on the top side is 0 degrees Celsius, and there is a heat flow that I have applied on the surface over here. Based on that, I have got the plot of the temperature to be these particular values, where there is very larger amount of temperature that is stored in most of the elements on the particular model. And if I would go to the total heat flux, so over here, the same kind of results which we were getting from a 3D model have been generated over here. But you can see how the particular optimization has been generated over here in a 2D model. So basically, this is also density based optimization itself that I have applied. Objective will remain the same itself that we did applied for the thermal conditions for 3D model, and those itself have been applied over here. And if I would go now to the topology density, so over here you can see how this particular optimization has been done. So it finds that particular heat flow for the particular geometry which we were using actually for the simulation can be optimized in such a way that the heat flow will not get affected over here if you use such kind of geometry, and if there is a particular 0 degree temperature that will be available on this particular region. So this way you can particularly even perform a 2D simulation as well. So usually performing a optimization is not much amount like much difficult, but this depends what kind of optimization process you are using. Usually lattice structure takes lot amount of time to generate the optimized results for any kind of model that you might be using, because lattice structure itself are very much difficult to develop and to generate. And even validation of those structure will create much amount of issues in the simulation. Then shape optimization is one of the better thing which will help you with morphing the particular model instead of removing the material from the geometry based on the conditions that you have applied, and it will provide more amount of strength as well to the particular model. So this way you can particularly go with any kind of optimization processes. The particular structural, thermal and the particular vibration simulation does remains the same. Just based on those results that you get from any kind of simulation, you can use it over here for the optimization purpose. So that's all for this particular session. If anyone has any kind of doubt, then please go ahead. So the last thing that was left out to be discussed over here was related to what kind of things that you can do next. So basically what all things that you need to know at the earlier whenever you go for the optimization process, that is you should know the ANSYS space claim so that you can modify the geometry. Any kind of geometry modification software is recommended to be known for the optimization process, because even you need to clean up the geometry later on. Then you need to particularly like have some understanding about structural and thermal simulations, then you can go with Ansys topology optimization toolbox. And we do have a particular after optimization process. We usually make the model use for the additive manufacturing process itself. So for a 3D printing, Ansys Workbench itself have a additive tool where you can particularly combine thermal and structural simulation for the additive manufacturing process. And we do have additive solution as well, where we do have three different kind of tools like additive print, prep, and additive science, where easily you can find out different kind of tools. Like additive print will help you with the machine settings and all other things. Additive prep will help you with particularly how much amount of support is needed to be applied for the geometry to 3D print, how much amount of distortion tendency, then how much amount of time it might take to particularly develop the model. You can select the particular regions from the orientation map, that how the particular model should be oriented on the XZ plane, or either a XY plane as well. So you can select those particular things, and you can reduce your particular build time or the minimum amount of support, and even the distortion. So wherever you will point out your cursor on, that will particularly change on these particular things for the model. So all these additive prep purpose tools are as well available in Ansys that you can utilize for the 3D printing. And additive science can be used particularly to do a microstructure level analysis of whatever the 3D printing process that you are carrying out. So this way you can particularly go ahead with whatever the models those are available in Ansys to particularly go from a scratch to the 3D printed model prototype. So all this process can be learned even through lot many number of resources. Those are available on the Ansys innovation courses, Ansys learning hub, and Ansys help documentations. So you can just go through them as well. So that's all from this particular session.